So what? Do you think that the theorem is now true? How would you prove it? So, true. Actually, we don't need induction here. Why? Because, let's say, suppose, so, true, here's the proof. Let G be a simple connected graph with n vertices and n minus, although there will be some induction, but we're not going to write it because it's, because you will hear induction when I say and so on. Whenever I say and so on, that's induction really here and there. Because if you want a really precise argument, then you must know how many times do you do that so on. So what? So G is a simple connected graph with n vertices and n minus 1 edges. So if it's a tree, we are done. What if it's not a tree? What's preventing it from being a tree? It's a simple. It's connected. The only thing that fails is what? It has what? Circuit. It has a circuit. So if G is not a tree, so let's assume that G is not. No, assume G is not a tree. Then what? Since it's connected and simple, the only thing that can fail is that what G has what? Circuit. What can we do then? Take one edge and cut it off. What happens? Is it still simple? Of course. Is it still connected? Yes, we had a theorem that says if I have a circuit and if I cut one edge, do I always have alternative? Yes or no? So that edge could be always whenever you wanted to use that edge, I have alternative path counterclockwise. So cutting one edge from a circuit never can ruin connectivity. We had a theorem before that. So remove one edge from this circuit. What happens? Now we got a tree or not? If we got a tree, contradiction. No. If we got a tree, that's good. What if we don't get a tree? Again, there is a circuit and keep cutting, and there are finitely many edges. So at the end, we must have something that doesn't have any what? That is connected with no circuits and simple. So at the end, we'll get what? Tree. So after cutting, after repeating the procedure, we get a subgraph, technically, G prime, with how many vertices? Do we ever remove vertices or just edges? So with n vertices and k less than n minus 1 edges. Why less than n minus 1 edges? Because I started with n minus 1 and I started to cut. So can I get more edges or less edges after cutting?
How did you start with n minus 1?
What's it?
What? It's not a tree initially, it's a circuit.
No, it says if a simple graph has n vertices and n minus 1 edges. So that's an initial assumption. So if I keep cutting, or maybe you don't want this k because of induction, let's say L. L less than n minus 1 edges. So what then? What about that G prime? Is this G prime a tree, yes or no? We said we stop cutting when we get a tree. So a subgraph G prime, which is a tree, with n vertices and L less than n minus 1 edges. But then, according to the one direction of the theorem, if that tree G prime has n vertices, how many edges does it need to have? n minus 1. G prime has n minus 1 edges because it is a tree at the end. And then when we plug that in, we get n minus 1 less than n minus 1 contradiction. So that's it. And that hidden induction is, we should maybe do induction on the number of cuttings. But doesn't matter. First time you cut, immediately you know that you are going to reach contradiction. So what's happening here? Just counting. If you see that it's connected, just counting vertices and edges, you can see if you have a tree. That's, by the way, why very often to check if your expression is correct, what do the programs do very often? Do they count left and right parentheses? And because when you do the typing, they always warn you that left parentheses is not matched with the right one, and that's actually exactly where you ruined your tree in the number of connections. All right, so we have a nice criterion to see if a graph is a tree, just counting vertices and edges. All right, here is that proof. So it goes both ways. So for example, let's look at this tree here. First, is it a tree, yes or no? Yes. And how many vertices do we have? They are labeled, so it's very nice. How many? 12. 12 from 0 to 11. And then let's count the edges just to see on it. So 3 here, 5, 6, 7, 8, 9, 10, 11 edges. So we just checked our theorem. By the way, what happened in this example? In this example, we already have something that we call the rooted tree. So when do we say that the tree is rooted? When one vertex is pronounced to be root of the tree, as I said, I required in the definition that tree has degree greater than 1. So that a root must have branching immediately, yes?
So they're like saying that one vertex is an ancestor to all other vertices?
Transitionally, yes, actually, yes. Because you see, V0 is not connected to V4 directly, but in a way there is a path from there. And so that one vertex is pronounced to be a root so that everything is calculated with respect to that root. Why is that a very good idea to pronounce one root? If you look at this, what can we do if we have a root? Then we can do the ranking among the members, like in the family trees. Oh, I forgot among the examples of trees. Of course, family trees are one very popular example of trees. So what happens here? Then we also say the following. We actually put the members of our tree on the levels. So here it is. Root is usually considered to be at level 0. And then we write all the children of that root, and that means all those vertices that are directly connected. So with that root, we say that they are at the level 1, and we also say that those members have height 1. So they are height 1 in that family tree in a way. And then what? All those that are connected with elements of height 1, but not on the previous levels, all new elements are now placed on level 2, and we say that they have height 2. So generally what? What is the height of the element? How would you make a definition of a height? I actually told you what it is, but what is the simplest definition? Yes, or the length of the path from root to that one. So that generally tells you which generation you are. How far are you from the first person? So how many paths exist from the root to that element? Is there only one path? and then you count how long is that path. So length of the path from the root to a particular element is called the height of the element. So for example, all these elements here have height 2. Why? Because path from V0 to V4 has length 1, 2. 2 edges is in that path. And all elements that have height 2 are placed on level 2. And then again, each of them might have children on, and those children on then on level 3. And finally what? Is there someone on level 4 here on this graph?
Yeah.
Yes, V11 is the element of level 4. And then this is a very good idea for rooted trees to actually have that hierarchical organization. Yes?
I'm curious if you had like a point V12 that points to V3, would that still make it? Would it still be a tree? 'Cause it's not a
V12 pointing to V3?
yeah, like
Yes, but then don't think that V12, because you gave it a name 12 would be here, V12 would be just here on the side.
Right.
As soon as you are directly connected to V3, you are level 2. The labels do not matter. You know, you thought I'm going to put it on the 6th level or 5th, whatever it is. No. Depending on who it's connected to, then that determines the level. And as I said, there's only one way to connect, otherwise you would build a circuit. So there are unique addresses. This is good to make addresses. You know. All right. And then here are again a little more definitions. So binary tree is a rooted tree in which I forgot to tell you terminology. Terminal vertex is the one that has degree 1. So terminal vertex means just gets connected to something and things stop at that one. Because if you have a parent and a child, you must have degree 2. Do you agree? One down and one up. But if you have degree 1, that means things stop at you, and those are called terminal vertices or leaves. So here, who is leaf altogether? And leaves could be on different levels. So is this a leaf? And then these two are leaves, and these two are leaves. So they are just, we have different lengths of the graph. All right. Vertices which are not terminal are called internal vertices. Is that clear? So each vertex is either terminal or internal. And then here is another definition. As I said, there are tons of definitions here. It's important to fix terminology. So binary tree is a rooted tree in which every internal vertex has at most 2 children. So there's only double branching or no branching at all. And then full binary tree is a rooted tree in which every internal vertex has exactly 2 children, which we often label as the left child and the right one. Why is that important, by the way? Because if you write a program, you know, and then you say, pick a child, but you must say which one. So for example, you write all the nodes in alphabetical order, and you say, pick the first one in alphabet, because you have to give him instruction without alternative. So you say, pick the first one in the alphabetical order, in that initial labeling, or something like that. The one that's first in alphabetical order will be called left child. The other one will be called the right child. They always say, pick a left one or pick a right one, whatever your construction wants to do. But as I said, if you have ambiguity, you have to resolve it in whichever way you do it, as long as there is no ambiguity. All right, here is an interesting theorem about full binary tree. And then the theorem says the following: let T be a full binary tree. T has an odd number of vertices. If the number of vertices is 2k plus 1, then k vertices are internal and k plus 1 are terminal. So basically, like a little more than a half are terminal, a little less than a half are internal. Why would that be true? That's not so obvious, I would say. So here it is. We'll go to do the proof, but let's see how to make this. Let's make a question. Construct a full binary tree with 7 vertices. Can we do that? How? What's it? Yeah, we start with the root, and then what? It's full binary tree. That means you can, I cannot go with the line, because it has to have, as long as you don't want to continue, you must branch. So what? Let's make it like branching. So here is 3. As I said, without this theorem, it might be a little harder to think of the construction, but let's see, this is 3. What we do now?
4, 5, 6, 7.
Branch one of them, so how much is this? 5, and then what? 6, 7, is that the one? All right. What about with 6 then? Sorry. How are you going to make it with 6?
Oh yeah, you just two initials. So
Two roots. No, you cannot have 2 roots. So you have a root, and then what? You have to branch. That's definitely. So here are 3. So if you want 6, one of them has to branch. Do you agree? So here it is. So this will make what? 5. And then if you want to make 6, what do you need to do? As soon as you branch twice, if you don't branch, you're going to stay at 5. If you branch, you're going to add 2. Every time you branch, you add 2. So can I make 6 vertices? No. And that's what this theorem says. So if you have a full binary tree, T has what? Odd number of vertices. And then if the number of, and what's interesting, so this is a good one. So 6, it cannot be done. 7 is fine. How about, let's say, 11? So what? Generally, what you can do, and that's always the simplest construction where you don't have even to think about it, is the following one. Branch. Here's your 1. Do you agree? And then for this one, whenever I branch, I add 2. And this one, I don't want to develop at all. So how many did I add? So I started with 3. Now I have what? 5. Branch this one. This will give me 7. Branch this one. This will give me 9. Branch this one. This will give me 11. Each time I added 2 new vertices, and then 2 at a time. And you can always do that actually going just fully left. So this is definitely something that's very easy to construct. Don't you agree? And actually, that's how proof will go. That whenever we have odd number of vertices, then we can make it. Yes.
Could you prove that this theorem is true by using induction to prove that every time you add a vertex, it's divisible by 2k plus 1?
No, every time we add the vertex, actually we have to, it's either stops or branches, and every time you have to add 2.
Yeah.
Yes, because there are 2 children if you decide to do anything else. So either you stop, you are terminal, or you keep branching. That means plus 2 plus 2. So that's it. If you start with 1, you must stay odd. But generally, that's kind of common sense argument. And then, as usually, we'll go and make a proof by induction. Oh, but there is something else that I forgot from the theorem to mention in the example. That distinction between terminal and internal. So here I have 11 vertices. Which one are internal? All these are internal. How many? 1, 2, 3, 4, 5. 5 are internal, and how many are external? 6. And it's always like this. Half, half, slightly less. that one extra odd one is on terminal. Why is that? So here is the theorem. Point 4.4. What? A full binary tree has odd number of vertices. If the number of vertices is 2k plus 1, k of them are internal, and k plus 1 terminal. Actually, no, I don't need induction on this. No, it goes directly. What? Proof. Let S be the number of internal vertices. Okay. How many children do they have? Because every internal vertex must have two children, because otherwise it's terminal. Because you cannot have one child. You either stop or you have two. So generally what? Those S number of internal vertices, they have how many children? 2S children. What are those children? Are they internal or terminal? Depends. Some of them will be, doesn't matter. But they have 2S children. But what else? Every vertex is someone, so when I list all the children, then who do I list actually? Who is there? First, so now 2S children, every vertex is a child of exactly one parent. Do you agree? So what is that telling you? Every vertex was mentioned here among those 2S children, and everybody was mentioned only once. No one was mentioned for two different parents. So generally, total count, every vertex is a child of exactly one parent, except who is not child of anyone? Except the root. The root. So how many vertices do I have? Those 2S here, and what else? Plus 1. So total count 2S plus 1. Here it is. That's it. That's the whole theorem. No need for induction or anything. And then what? How many of them are terminal then? If total is 2S plus 1 and S are internal, then terminal are what? S plus 1. So everything works. Once again, so if you have a full binary tree, it must have odd length. Yes?
The way this is written, aren't you assuming the conclusion? If you're saying let S be the number of internal vertices?
No. I'm just saying F. That number. I call it, on purpose I didn't call it K so that you can say, I call it S.
Okay.
So because you must have, do you need to have internal vertices?
Yeah.
I count them and I call that S. Can I do that? I'm not assuming anything about S.
Okay.
And then I'm saying that the total count is 2S plus 1. So I proved what?
Okay.
The other way around, actually, from number of internals. So it's all clear. All right, let me go back to this question. So, so if it's full binary tree, the length is 2k plus 1. Can we prove the following? How about in a way converse? So question, does for every odd number of the form odd number n exists a full binary tree, sorry, a full binary tree with n vertices. Like I did there, for 11 we made it for 7. If someone says 27 vertices, and you have a couple of homework problems, 27 vertices, can you make a full binary tree with 27 vertices, yes or no? How? Basically, I'm not going to write it as a proof or as a theorem. Can we always do it like this? Completely left inclined tree. So always just add two more to the left by induction or however you want to do it. Yes?
What about 1?
Yeah, it's greater than 1, right?
I would say?
Actually, greater than 1 and greater than 1.
No, 1 is considered a full binary tree.
But it doesn't have to branch.
Doesn't have roots.
What's it?
Doesn't have to branch.
If it branches, it's just terminal limit. Oh, contradicts the definition that it has to branch. True.
Doesn't have roots.
No, would be okay in their definition, but I made definition that degree of the root must be at least 2. So if degree is at least 2, then you must branch. So yes, degree for every odd number n greater or equal 3. All right, you learned this course well. That's now you can catch little finesses when they appear. Very nice. Good. So as I said, I'm not going to write this proof because it's quite obvious. But I don't like something about this construction. Sometimes this tree doesn't look nicely balanced. Why? Because it's too high for our purposes. Do you agree? So the question is, can I make always a balanced tree? What would be a balanced tree? So let me ask you a couple of questions in this direction. So this one is completely on the left. All right, so question 1. Is there a tree of height 5 with 71 vertices? Yes, so I'm not allowing very long branches. I just want more balance so that all branches are as short as possible, so that it's so that it develops in a balanced way. Do you understand the reasons for that? Yes.
Is height referring to 5 vertices?
No, height is the way I mentioned it here. You see, height is the length of the path, so from certain element to the root. So this element has how many path? How much is height? 1, 2, 3, 4. So height is how many layers does it have actually? So if I have only 5 layers, can I build such a tree? Why not?
Because you need 5th.
Yeah, to the 5th is 32.
So 2 to the 5th
Gives
minus
you
1.
Yes, so generally, So you see, the most I can do, it's complete full binary tree. That means everybody branches. I never stop until I reach 5. If I do that, like on heads and tails, then what happens? Here I have 1. On level 1 I have 2. On level 2 I have what? 4. Then I have 8. And then on level 5, which is the last admissible level, is 32. Do you agree?
Yes.
But then 32 is what? Terminals at most. So terminals are less than or equal to 32. Internal is less than or equal to 31. The most I can do is 63. And 63 is the full binary tree. That's like all the binary numbers, like with 5 digits. Do you agree? And then what? You can go with the, what, 0, 0, 1, and so on. So two options here, two options here. So we have 64 options, except the option 0, 0, 0, when you don't have points at all. So generally what? There are really, so you cannot make 71 vertices with such short height. So what would be the theorem that you would say? How high has to be 3 for a given number of vertices? So if you have what?
Minus 1 is greater than.
So if n equals 2k plus 1, do you agree? Then how many terminals do we have? K plus 1. K plus 1 has to be less than 2 to the h. So if that's true, then you can build that tree, because that's the number of terminals, and on the h level you can make 2 to the h because of that branching. So here is the necessary condition that you can balance your tree. So k plus 1 number, which is number of terminal vertices, must be less than 2 to the h. So the question is, how would you, so generally what? Let me now make this a little better. What's it?
How would you write a theorem for the number of total vertices?
Oh, yes, we can. Why? Because it's this. What's k plus 1? We take n plus 1 over 2, less or equal to the h, because n is 2k plus 1 is 2k plus 2. So here it is, n less than or equal to the h plus 1 minus 1. I can write it like this, but I prefer, because here we see 3 better, if you see the upper level. What else is there? So the question is, so if, what if I have like a question? Construct a tree. With 21 vertices. Construct a full binary tree. With 21 vertices of minimal height. How would you do that? That might be interesting. Why? Because sometimes, your resources are better used if you have shorter branches, you have loss of signal and something like that. So generally, you don't want those. Theoretically, they give you an answer and proof, but you want something that's more balanced. You don't want to go far unless necessary. So what? So generally, how many terminal vertices are there? 11. Do you agree? Because 21 is, so k is 10. 11 terminal vertices, and so 11 is less than or equal 10 to the 4th. So what? I can do it with height 4. And how can I do it? Here is one easy way to describe. I describe more complicated way in my notes, and I explain why. So how would you build a tree with the 21 vertices of height 4? Here's the way to do it. Actually, the way I thought of it is, first enclose it up to height 3. You might need somewhere, yes, that's the same thing actually, yeah. So I thought of it this way. Generally, when you see this 2 to the 4th, then you can do the complete binary tree like this. How much is this? This is length what? 1, 2, this is length 3, and here's length 4. Exactly. So here it is. That would give you what? That would give you 16 terminal and 15 internal. Do you agree? And then what do you do? you just start, which is 31, and I didn't want 31, I want what? 21. So I need to reduce 5 times. So what do? I just cut those. So cut this. What is my loss? 2. Although this one was internal, now it becomes terminal. So that keeps balance. I'll erase 1. I'll erase 2. I'll erase 3. I'll erase 4. I'll erase 5. That's it. Although Julian had basically the same idea, go to the level below, so fully do 2 to the third, and then see how much do you need to add, and then you keep adding here as many as needed. So generally that would be not from 31, but actually what? From 8 and 7, 15, and then from 15, add 3 times those V's and be done. And then, yeah, so that's how you can construct. These 3 of minimal height, as I said, this is the most balanced you can do it. And it has often advantages with respect to these 3. All right. I think that we have decent idea how these objects behave. Let's at least start a little bit the story about, is everybody okay with this if we go a little bit further in section 5 so that we have a little less work on Wednesday? All right. So what is the idea in 7.5? The idea is to do something called spanning tree for a graph. So 7.5, as I said, just a little introduction. So what is the idea with the spanning tree? Sometimes we have a graph, and it is not a tree. So what do we want then? Sometimes it's helpful to just cut off unnecessary edges and just reduce it to a tree. And then what? So when would we call that tree a spanning tree? So it is a subgraph of a graph that is a tree and something else and contains all the vertices, because you can just reduce number of vertices and you have something local. You want all the vertices to be still connected, and of course you cannot have a subgraph. You cannot do that if your graph is not what? Connected. So if your graph is connected, then you want to keep it connected, but without unnecessary routes. So you want unique paths, and that's how you reduce a graph to become a tree. And that's what we'll do on Wednesday. So we'll see how do we reduce a connected graph, connected simple graph to become a tree, and then we'll see different methods to do it. So spanning trees. So every connected graph has a spanning tree. Is that true? That's actually the idea that we used in one of the proofs. If it's connected and simple graph, then what do? If it's not a tree, what do? Okay. It has a circuit, cut an edge, it's still connected. If it's not, and keep doing it until finally you cannot, there are no circuits, and that means you will end up with a tree. Is that clear to everybody? And then what else? It says every 2 spanning trees of the same graph have the same number of edges. Is that true? Why?
They have the same number of vertices?
If they have the same number of vertices, and then because of this theorem, if they have some number of vertices, number of edges is n minus 1, So that's really true. So that's simple. So here is one graph, and then is it connected? Yes or no? And then the question is, how do we build a spanning tree? So what are we going to do? Whenever you see a circuit, you can cut an edge. So for example, which do we see a circuit here? Yes or no? Then we can cut an edge, and then so let me describe the stages. So here it is. So the first thing, we'll take this edge off, and it will have that triangle. We'll have this, and we'll have this, and everything else is there. Is it still connected? Yeah, but it's not a tree, so what do we do then? Cut off another edge. Which one? Doesn't matter. Actually, what? Yes, it is connected either way. Whichever one we cut. For some reason, I like this one to cut. So here is your triangle. Here is this. Here is this. So I like this to have. And then finally, what? We cut one more edge, and then